Hey, this is Mr. C here. This is part one of a two-part series from the problem set. We're going to work through problems 41 and 45 from the problem set. So let's go ahead and jump right in and start with number 41. The problem reads, a 6 centimeter diameter horizontal pipe gradually narrows to 4 centimeters. When water flows through this pipe, I'm going to go ahead and underline water. At a certain rate, the gauge pressure in these two sections is 32 kilopascals and 24 kilopascals, respectively. They want us to find the volume rate of flow. So when you hear the words volume rate, we should be thinking continuity equation. What we should also be considering, because we're talking about different pressure changes, is Bernoulli's equation. So it's pretty clear, in order to solve this problem, we're going to use both the continuity equation and Bernoulli's equation to solve. Okay, before we jump in, one last little bit of notation. I'm going to use the subscript 1 to represent the larger section of pipe, and I'm going to use the subscript 2 to represent the smaller portion of pipe. So, I said we're going to use the continuity equation and Bernoulli's equation to solve this. So let's go ahead and jump in with the general continuity equation. So, to represent the volume flow rate, so big V, I can represent that by the cross-sectional area of the pipe times the velocity of the water through the pipe. So the volume flow rate can be represented by A1 V1. Also, because we have the continuity equation, we know A1 V1 equals the cross-sectional area of the pipe through point 2 times the velocity of the water through 2. Now, we were given the pipe's diameters, so we can represent the cross-sectional areas in terms of a useful thing, maybe the radius. So what I'm going to do is I'm going to represent the area in terms of the radius, and I want to solve for V2 in terms of V1. So I'm going to do that all in one step. So V2 equals V1 times, we're going to have pi R1 squared over pi R2 squared, which clearly simplifies to V1 times R1 squared over R2 squared. And there we have it. We've represented the velocity of the water through pipe 2 in terms of the velocity of the water through V1 and the radiuses of the two pipes. Now what I want to do is go ahead and write the full Bernoulli equation, and then I'm going to eventually plug in my solve for V2 and see what happens. So the full Bernoulli's equation is atmospheric pressure plus pressure inside the larger pipe plus rho GY1, there's our potential term, plus 1/2 rho V1 squared, there's our kinetic term, equals atmospheric pressure plus pressure inside pipe 2 plus our potential term, rho GY2, plus our kinetic term, 1/2 rho V2 squared. Now, it said in the problem that the pipe starts horizontal and remains horizontal, so our heights remain the same. So as far as the potential term, we see that those two pieces cancel out. We also have that the atmospheric pressures cancel out because we're only talking about the pressure inside the pipe, so those two go to 0. And so what we're left with is the pressure in the first pipe, the kinetic term in the first pipe, the pressure in the second pipe, and the kinetic term in the second pipe. So what I want to do is I want to try to solve now for V1 in terms of all those pieces, okay? So I'm going to go ahead and I'm going to solve for V1. But first, before I do that, one last little point. I have this V2 here. Recall that above we solved for V2, and we said that V2 equals V1 times R1 squared over R2 squared. Therefore, V2 squared is obviously just going to square all those terms. So again, what I'm going to do now is I'm going to solve for V1 in terms of everything we have here. So, sparing you guys the calculations, I'm going to go ahead and I'm going to say V1 equals the square root of 2 times P1 minus P2 divided by rho of water times r, oops, r1 to the fourth power divided by r2 to the fourth power. Those fourth powers came about because we squared the square term over here, minus 1, and there we have it. V1 in terms of the whole piece, in terms of everything else using Bernoulli's equation. Recall, we wanted to find the volume flow rate. So in order to get the volume flow rate, we need A1 V1. Because remember, V equals A1 V1. So what that equals is A1, which is pi R1 squared, times the square root of everything we just have here. 2 times P1 minus P2 again, over rho R1 to the fourth over R2 to the fourth, minus 1. Now it's just a matter of going and plugging in. My radius of the first pipe was 3 centimeters. We were given the two pressures. Density of water, that's 1,000 kilograms per meter cubed. And then again, just plugging in my two radii. When it's all said and done, going through the calculation, I get a volume flow rate of 5.6 times 10 to the negative 3 meters cubed per second. All right, and there we have it. So this problem is a little tricky. It involved using the continuity equation and Bernoulli's equation. But we can see the basic steps were just to solve for the velocity in terms of the other velocities in the cross-sectional areas, and then just simplify and solve Bernoulli's equation. Okay, hope that helped you guys out. Stay tuned for part 2.